In general, what do you think increasing on a function means? Going up, right? So as you look at the graph from left to right, it's going up. So f of x is increasing from -2 to 5, and then it increases again when x is 7 to infinity. So we do use x values to describe increasing and decreasing. Oops. Yeah. Oops, sorry, negative. Oh, sorry, that's +2, isn't it? 2 to 5, right? Thank you. So 2 to 5, it's increasing. And then from 7 to infinity, does that make sense? Yeah. Okay. Sorry, I don't know why I put a negative there. That's crazy. Crazy talk. All right, and then it's decreasing from -3 to 2, and then 5 to 7. So let's talk about the fine print about increasing and decreasing intervals. There is often confusion about why we include the endpoints when discussing increasing and decreasing intervals. The confusion really is due to a misunderstanding of what we mean when discussing intervals of increasing or decreasing behavior. It is important to understand that we are not ever claiming or discussing a single point on a graph as increasing or decreasing. How could one point be increasing or decreasing anyway? Rather, we define increasing as follows. A function f is increasing on an interval whenever f of b is greater than f of a, for all b greater than a. More simply, we must include all x values where the current point is higher than the point right before it. This means that even at the points where the graph seems to stop increasing, we must include those x values in our interval, since that point is still higher than the point right before it. We can define decreasing in a similar way, which is why we use closed intervals whenever the function is defined for both increasing and decreasing intervals. So when we include the endpoints in our intervals, don't be confused and think we are claiming that the function is increasing at that point. We are only stating that the point is still higher than the point right before it or after it. So looking at the graph of f of x, it is relatively easy to see when the graph is increasing or decreasing. However, in calculus, we generally will not have a graph of f to look at. So what properties of f could help us determine the intervals where f is increasing or decreasing? Well, the rate of change, or the derivative. So we're going to circle back now to what we talked about in 5.2, critical points. Remember, f of x, if f of x is defined at x equals c, that's an important piece right there, then f of x has a critical point at x equals c if f prime of c is 0 or f prime of c is undefined. So let me give you about a 2-minute head start, and I want you to try to find the critical point in example 1 and example 2 if they exist. When I do these, I stop and think about my domain. And in example 1, when you have a fraction or a rational function, you know your I remember to circle back to it before I'm done. So I'm getting low d high minus high d low over low low. And I want to know where that derivative is 0, so I would get x plus 2 minus x, so that's 2 over x plus 2 squared. So h prime of x never equals 0, right? Because the numerator is 2. And then h prime of x is undefined at x equals negative 2. So we might think x equals negative 2 is a critical point, but what do we know? It's not part of the domain of h of x, the original function. So there's no critical point because h prime of x never equals 0 and x equals negative 2 is not in the domain of h of x. In example 2, what do you notice? You're given the derivative, right? Oh, that's not f of x. That's actually the derivative, f prime of x. So what do we need to do? Just find where it's 0 or undefined. So you would just change that so you don't need to find the derivative. We were given the derivative. Well, this would be x minus 1 is 0, so x is 1. And what happens with e to the 2x equals 0? Remember what e to the x in my Algebra 2 classes? We do our arms all the time. Here's e to the x. And it has a horizontal asymptote at y equals 0, so does it ever touch the x-axis? No, so this piece does not produce, and it's not undefined, it just does not equal 0. So I have a critical point at x equals 1 because f prime of x equals 0 at x equals 1. All right, so critical points are critical. And now we're going to talk about increasing and decreasing intervals using calculus. So consider the continuous function f of x. So it does have to be continuous in order for this to hold. Number 1, if f prime of x is greater than or equal to 0, then we can say that f of x is increasing on that interval. If f prime of x is less than or equal to 0, then we can say that f of x is decreasing on that interval. So I'm going to slide back up here, and I want you to stop and think here a moment. Do you notice that the slopes were negative all along here? And it was decreasing. Slope positive, it's increasing. Slopes negative, decreasing. Slopes positive, increasing. Like that's the y. So to find intervals where f of x is increasing or decreasing, you go through these steps. Find the derivative. Find where the derivative is 0 or undefined, or in other words, find the critical points. Then you're going to create and label a sign chart for f prime of x to test intervals around the x values from step 2. And then you're going to interpret the sign chart to find the appropriate intervals. Here's a helpful tip. If you're given a graph of f prime of x, you don't need a sign chart because the graph of the derivative is the sign chart. So let's look at example 3. I'm going to give you about a minute head start, and I want you to find the derivative, find the critical points. again, in example 3, find the derivative, the critical point. Then I'll lead you through the number line test. All right, did you get x equals 3/2 as the critical point? All right, this is a parabola, so you do want to think about that. So you're going to make a number line, and because we're eventually going to get to second derivative number lines, let's go ahead and get in the habit of labeling that this is g prime of x. So what you're going to do is we're going to pick a number, let's say 2, and you're going to plug it into the derivative. And I don't care what the number is, I only care about the sign of the number. Is it positive or is it negative? So this is positive. Then let's pick a number to the left. I like 0 whenever I can use 0. So that's negative. So watch what we're going to say now. G of x is increasing on the interval 3/2 to infinity because g prime of x is greater than or equal to 0 on that interval. G of x is decreasing on negative infinity to 3/2 because g prime of x is less than or equal to 0. So it's super simple, okay? Students typically like increasing, decreasing, very straightforward. All you do is find the derivative, set it equal to 0, find your critical numbers, do a number line test to see where the derivative is positive or negative. Where the derivative is positive, the function is increasing on that interval, and where the derivative is negative, the function is decreasing. So the derivative is telling us about the original function. Questions on that one? All right, example 4. Now I'm given the derivative, okay? So pay attention to that. I'm actually given the derivative. So to do my critical numbers, they've already done the hard work for us. My critical numbers are 2 and negative 1. Then we're going to make a number line, and we're going to put those on there. And I'm going to pause a moment, try to give you a head start on determining the signs. And then if you're a fast worker, try and write where h is increasing and decreasing. All right, so when I did this, I actually got minus, minus, plus. Did you get that as well? So, h of x is increasing on the interval 2 to infinity because h prime of x is greater than or equal to 0 there. H of x is decreasing Now watch how we're going to say this. You have to really think about your functions. This is a polynomial. So if you remember what you did in pre-calculus, now just like it all comes together here. I don't have a break in the graph at -1. You do have to consider, do I have a vertical asymptote there? Is there a removable discontinuity? This is a continuous function. So I'm going to describe the decreasing from -infinity to 2 because h prime of x is less than or equal to 0. But you do have to consider breaks in a graph. Because if I had had a vertical asymptote at x was -1, then I would have written 2 intervals. Does that make sense? And then I wouldn't have included the -1 because it's a break in the graph. All right, go ahead and try example 5. Try and get as far as you can before I work it out. You're going to have to remember some unit circle trig here. Please don't use a calculator. What you remember. All right, so I'm going to do k prime of x, which would be 2 cosine x minus 1. I'm going to set it equal to 0. And then I'm going to get cosine x equals 1/2. All right, pay attention to the interval. This says on the interval 0 to 2 pi, but not including 2 pi. So all students take calculus. All students take calculus. Cosine is positive in the first and the fourth quadrant. Since I'm in my first quadrant, that's my reference angle. So what would be the angle in the first quadrant where cosine of that angle is 1/2? Pi over 3. If you're struggling, go back to your 30-60 right triangle. I just always remember that sine 30 is 1 over 2. Then cosine, to get 1/2, would be coming from the 60 degrees. Then I have a second angle in the fourth quadrant that's 60 degrees away, or pi over 3 away. So if 2 pi is 6 pi over 3 and you're rotating 1 pi in, that's 5 pi over 3. So now we're going to do our sine chart. So what you're doing is you are plugging in a value, and let me label this. This is k prime of x. So let's say we pick, I don't know, pi over 6. So that'd be 2 cosine pi over 6 minus pi over 6. Whoops, not pi over 6, minus 1. I'm plugging into the derivative right here. So that's 2 times square root 3 over 2 minus 1. Well, square root 3 is definitely bigger than 1, right? We at least know that. So that's going to be positive. Then let's say we choose, I don't know, you can do pi over 2 or pi. Either is okay. So let's say I picked pi. That's -2 minus 1. That's minus. Then let's suppose we pick 11 pi over 6. That's 2 times radical 3 over 2 minus 1. That's positive. All right, so do you see the foundation of the unit circle here? Okay, you're really supposed to know that. You can come up with Quizlets to help you. You can Google it and have all sorts of unit circle practice if you're feeling like you have forgotten some of that from pre-calc. I mean, that's on you. So you've got to do some outside work time on that. So here we go. I'm going to say f of x is increasing on the intervals 0 to pi over 3 and 5 pi over 3 comma 2 pi. Now, why would I be putting a parenthesis on the 2 pi when I did the bracket everywhere else? It's not this. They're asking me to not include 2 pi. That's why. Okay, that's the only reason why. And then f of x is decreasing on the closed interval pi over 3 to 5 pi over 3. And I should write because the derivative's negative there and it's positive in the other spot, but I was kind of scrunching here. Again, this is not difficult, but if you don't remember your unit circle, then this is unbelievably difficult. So you have to decide, this is an individual situation, is if you have to go back and do some work, go back and do the work. All right, so here's an AP exam tip. Be careful when using graphs. If the graph given is f prime of x, then f prime of x greater than or equal to 0 whenever the graph is touching or above the x-axis. So in example 6, it says consider the graph of f prime of x above, where f prime is the derivative of f. Find the intervals where f is increasing and decreasing. So I'm going to pause a moment and give you a head start. This is now the graph of the derivative. Look at that exam tip to help you as you try to determine where f is increasing and decreasing. And go ahead and go on to example 7. We're just finishing the notes. let me go ahead and let's see how we did on this. In number 6, f of x is increasing on the interval negative infinity to negative 1. Do you notice at negative 4, it does touch 0, but that's okay. It's greater than or equal to 0. And it's not a break in the graph. So it's going to be increasing. Whoops. Which one am I on? Sorry, let me fix that. Yeah, no, that's right. Negative infinity to negative 1 because it's positive everywhere. And then it increases again 1 to infinity because f prime of x, f prime of x is greater than or equal to 0. So it is so tempting to see where the graph decreases, like when you're looking at the derivative and you think it's decreasing. It's just where the derivative is positive. So then it's decreasing on the interval negative 1 to 1 because f prime of x is less than or equal to 0. Did we get that? Can you give me a thumbs up? Got it okay? All right, then in example 7, this is again g prime of x. So g is increasing on the interval negative infinity to 1 and 3 to 10 because g prime of x is greater than or equal to 0. G of x is decreasing on the interval 1 to 3 and 10 to infinity because g prime of x is less than or equal to 0.
Multiple, for example, for three places, did you just